with Dr. Ratti.
Hello, I am Dr. Claudia Ratti and I am a professor of physics here at the University of Houston, and I taught the theory component of NuSTEAM, which is also related to my research. I do the theory of Quark-Gluon Plasma and the strong force.
And what we are going to learn this week?
We are going to learn everything about, the phase diagram of quantum chromodynamics and the strong force and what we can do to solve it numerically and how it relates to the experiments. So lots of cool stuff.
Okay, thank you so much.
Thank you.
My name is Dr. Jamie Karthein. I am an ascending NSF postdoctoral fellow at MIT, and today I wanted to chat with you guys in NuSTEAM about the most important topics when it comes to how to prepare a CV, how to prepare your applications for graduate school, what are the most important factors to consider when going to conferences and when trying to expand your network, and I'm happy to be here today.
Yes, it's coming back. It's coming back.
It's coming back. Okay.
We make other things besides Ubuntu, but that's sort of the thing that we're
They generate these gravitational waves. And actually the signal that we saw so far was just from this phase. So after they collide, they have this kind of electromagnetic signal also that you can see, and then the core.
Hello people, I hope you're doing well and had an excellent weekend. It's time to share everything I learned during week 4 of the NuSTEAM program. This week was a little bit lighter. We had no class on June 19 because of the Juneteenth. Most of our sessions were talks from guest speakers who shared their experience in the scientific field, their career journeys, and what we can expect if we follow the similar path. Since we have that day off, me and Lisa, we went to NASA and we was very excited about it. We learned so much. NASA is incredible, the Space Center of Houston. I recommend you 100% to go. But yeah, we start this week with Dr. Ratti, who gave us a review about everything we learned so far So she explained the standard model of elementary particles, including leptons that are electrons, muons, taus, their corresponding neutrinos. The important thing about this week for these particles is that this particle doesn't feel the strong force. In the other hand, quarks, the particles that make up protons and neutrons, there are 6 types: up, down, charm, strange, top, and bottom. And these particles can feel all forces, all the 4 fundamental forces. The important part about these particles is that quarks cannot exist freely in nature, so they are always confined inside larger particles like protons, neutrons, or pions, kaons. She also reminds us about the 4 fundamental forces and the 4 carriers. The photons carry the electromagnetic force and affects all the charged particles, so it doesn't affect neutrinos, for example, or neutrons. Then the W and Z bosons are the force carriers for the weak force that affects all the particles. Then the gluons, very important, that carries the strong force, and this only affects the quarks. And finally, the gravity that can be negligible at the particle scale since they have barely tiny mass. What I found super interesting is how the strong force behaves. So it gets more stronger when you try to separate quarks. For example, I have this rubber band. When I stretch it, it becomes more harder, and when I release it, it becomes more soft. So at some point, the energy you use to pull the quark apart becomes so intense that it creates a new quark-antiquark pair from the vacuum. Also, we went more deeper into the quantum chromodynamics theory and the concept of color charge, which is kind of the electric charge, but it has its own rules. So, for example, the quarks, all visible particles, must be color neutral. It means that all the colors that the quarks have must create white. The baryons have 3 quarks, and H1 has color red, green, and blue, so all 3 colors makes white. And the other hand, mesons have 1 quark and antiquark pair, so they are complementary colors, so they make white or cancels out. And actually, this is nothing related with the actual color of the particles, it's just analogous. Then this week we talked a lot about the Quark-Gluon Plasma, the QGP. This is the state of matter formed when the nuclear matter is heated and compressed so much that quarks and gluons are no longer confined. So in the rubber band example, when I stretch it, it's harder. When I release it, it becomes weaker. So it happens the same with the Quark-Gluon Plasma. When you compress them, it becomes weaker. They act like they are free. So also this help us understand the strong force and what the early universe might have looked like, since the early universe was the matter was in a Quark-Gluon plasma phase. The QGP is recreated at huge labs like the Large Hadron Collider at the CERN and the RHIC in New York by colliding heavy ions beams like lead or gold at a speed very closely to the speed of light. This generates enough energy to create new particles in this state of matter specifically. So more in depth, we focus on the QCD phase diagram, which is basically the behavior of the nuclear matter under the extreme conditions. As I told you, the extreme temperatures and pressure is kind of related with the phase diagram for water. They use so much this example. They have the solid, liquid, and gas phase, but for protons and neutrons specifically. So the main question to solve about this topic is, where is the critical point where the matter changed from confined particles as the protons and neutrons to the QGP. So we are trying to find this critical point depending on density, where it changed in transition and change in phase. Also, this diagram shows us that the transition from hadronic matter to quark-gluon plasma, we need temperatures 100,000 times hotter than the sun's core. But in actual collisions, the temperature that we can reach is 340,000 times the sun's core. We use this temperature because the quark-gluon plasma lasts about 10 to the power negative 23 seconds. Have enough time to study this quark-gluon plasma, but essentially we cannot study it because we cannot measure the temperature when it's in this phase. That what we measure is all the particles that came out after the freeze out stage. There are two types of phase transitions. The first order transition, that is a sharp change in properties. For example, boiling water, when you have these both phases, the liquid and the gas, and can exist at the same time. So this is called the first order transitions, and we can see it in the phase diagram as a line. And then exists this other phase called the second order transition, or the crossover, that is more smooth, is gradual change, and you cannot see the difference. For example, in the water, you cannot see the difference between the gas state and the liquid state. So for this week also, they assign us a specific project that we need to do an explanation about any topic that we are interested in, and we have to do a scientific presentation. So for my topic, I chose the QCD phase diagram, specifically this topic for this week, because I found it super interesting how you can change in confined phase inside the baryons to this phase called the Quark-Gluon Plasma. So I'm working on it, and I'm going to show you probably when I finish next week. So we are going to present it the last week that we are here on Wednesday, I guess. Also for this week, we, as I said, we also had so many speakers, and they are so amazing, and their lives are so interesting. They talk with us, give us some tips about the scientific path and career that we can follow. So the first speaker that we met was Dr. Jamie Karthein from the University of Houston, that is currently doing his postdoc at the MIT. She talked with us about the life in academia and how to apply to grad school, and also she gave us some tips for giving conferences. She also shared a lot of information about fellowships and opportunities, and honestly this made me start thinking seriously about grad school. I haven't considered it before, but I'm going to think more about that. And we met Dr. Minerva Betancourt. She is originally from Venezuela, and I was so excited because in this program I met so many Hispanic people, and that makes me so proud of it. She told us about her journey as a foreign scientist. She worked on the prototype for the NOVA experiment, now working at Fermilab. She is mentoring students from the Sully program, and I found her experience really inspiring. Also, she talked with us more about the Sully program. The students that are there, they do their own research, to be theoretically or experimentally physics. So also it made me consider applying the Sully in the future. Maybe our next video blog will be at the Fermilab. Then we met Dr. Erin Conley. She showed us how the physics fits into her work as a technical author at Canonical. Also, she used to work at the Dune experiment, and her path showed me how diverse science career can be, and how you can follow so many different paths and not only go strictly into a lab. And finally, we met Michael Kahangirwe. He's a PhD student. He shared his current research on the equation of a state of strongly interacting matter. And also he answered a lot of our questions with so much clarity, and now thanks to him I had this topic more clearly and I can speak more clearly about it. So this week wasn't as heavy as the previous ones, but I still learned a lot, especially about the QCD, about grad school, and how science careers can take many forms. Also made me think about which path I'm going to follow since I'm a junior student right now. And I want to thanks again to Dr. Ratti, Dr. Karthein, Dr. Betancourt, Dr. Conley, and Michael for sharing their stories and inspiring us to clarify all our doubts and be so kind with us. So yeah, I see you next week and I hope you enjoyed this video. Thank you for following my path and stay tuned with my videos. Bye.